Hello, everyone. I cannot
Hello.
speak Thai for sure, but I think I see one old friends here,
Yeah,
Professor
sure.
Tarawut, right?
Hello, Sean.
How are you doing? Yeah, I
Yeah,
think
as
never see
well.
you for more than 10 years
Yeah.
already.
So long time no see you, right?
Yeah. I think maybe sometimes I should go to Thailand and visit you. So are
Sure,
you in
sure.
Konkan University?
No, I moved to the Konkan. It's not it of Thailand.
Okay.
Okay. But
All
it's
right.
close. Okay.
Okay, all right. So thanks for inviting. Yeah. Let's look at Dassault long-term commitment to simulations. Yeah, you can see our commitment actually started way back in 2000. Yeah, where we actually started with the design simulations. So as some of you might know, yeah, SolidWorks and CATIA, they are actually a CAD tool, but we already embedded all these kind of simulations features inside this software already. But then, we know that this is not going to fulfill our objective. So what we did is, we actually acquire another software called Abacus. So Abacus is actually a specialized tool that is used for the mechanical simulations. Okay, and then we found out that it's actually not sufficient. Yeah, we need to go into the system simulations. Yeah, where we have this eyesight, Timola, Ginsoft, and then we expand to industry solutions like Tosca, FESafe. So whoever who is in the mechanical field, you should actually heard about all these brand before. Okay, but I think today's focus will be on the electromagnetics and fluids. Yeah, you can see that CST was actually acquired by Dassault System in 2016, late 2016. Okay, and so of course today I'm representing Dassault Simulia, to share a little bit with you on our EDA topics. So how are we going to deal with these PCB boards if let's say we have them? So in fact, if you go to industry, you can see a lot of people try to talk about SI, PI. Yeah, some of them try to talk about EMC. So all these kind of things can be easily done in CST. Okay, so uh, that is the reason I'm here today. Yeah, I'm going to share with you PCB and electronic designs analysis using CST Studio Suites. So a little bit about myself. Yeah, I joined CST back in 2007. Yeah, so that's why I know Professor Sarah Woods. So at that time we were working together. So it was actually quite fun. So I'm actually looking forward to visit Thailand again in the near future. Okay, so let's look at what we can do on this PCB board. Okay, of course, if you want to proceed with the simulations, the first thing is we need to import some structures inside our simulation tool, right? So as you can see, the import, we can actually divide it into two parts. The first one is electrical, means it's actually the layouts of your PCB board. And then second one is the mechanical CAD tool. Yeah, mechanical CAD means something like, your mobile phone or something like that. Okay, as soon as we import this PCB board inside, we can actually do various kind of analysis. For instance, we can go with this power integrity analysis. Yeah, is more onto the quality of your power planes, and then we can proceed with signal integrity. So it is more concentrating on the quality of these particular transmission lines. So once this is done, or I wouldn't say once this is done, I would say it's done parallel as well. Yeah, you can see that whoever is dealing with the PCB boards, you probably need to deal with the EMC as well. So EMC is something very, very important. Why? It's because if you do not pass the EMC, perhaps you are not able to sell your electronic products to the markets. Okay, and then uh, when electrical performance is already considered done, the next thing we have to consider is the thermal simulations. So if let's say you are, exciting with a very high power, so is it going to be very hot? So whoever is using these particular phones, when you are using it for 30 minutes or 1 hour, is it going to be hot? Is it going to hurt your hand? So this is something that we can actually perform in this simulation software. Well, so a little bit about the import possibilities. You can see we divided it into the E-CADs and M-CADs. So you can just name it. We can actually import it into our CST Studio Suites. No problem with that. Okay, but I think today we'll focus a little bit more on the E-CADs. Where we have to import in the PCB boards. And then we will proceed with the analysis we mentioned just now. Okay, so this is what we imported into our 2.5D simulation tool. You can see that, there are many features over here. Yeah, I'm not going to go through every one of them, but I mean, the reason of showing this slide is just to let you know, yeah, perhaps what you are seeing in our tool is almost similar like what you are seeing in the layout tool, except, yeah, we do not do that much of a designs in the layouts. So what we are interested to do is import into our tool, and then we are going to perform some analysis. Okay, so of course, when you want to perform some analysis, you need to have exact informations, like the stack up, yeah, the components, yeah, the nets, yeah, signal specifications, etc. and etc. Okay, so a quick things you can do when you try to import the layout into our tool is, you can actually use this impedance calculator. So what it means is actually we are always interested to control the impedance of our signal nets in the PCB boards. Okay, so some of the signal nets, it can be single-ended. Some of the nets, it can be differential lines. So we are always interested to adjust the, the width of these transmission lines. Yeah, and we are also interested to look at the heights of this transmission line as well. And of course, the next thing is we have to determine whether this belongs to the microstrip lines or strip lines. So all this is going to influence our impedance. And this is the impedance we have to control as well. Why? It's because the components we have, they have this, they have their own impedance. So if let's say the transmission lines impedance is not matching with the components impedance, then we are going to have a discontinuity. Then end up we are going to have problems with the signal quality, right? So this is something, a basic things, yeah, where we have to calculate, or you can actually design everything by yourself. Yeah, just use your hand to calculate everything. So a tool in this PCB Studio is just to simplify your works. Yeah, you can do everything inside the software so that you can get a quick results. So as soon as we import this particular board into our 2.5D or PCB Studios, we can actually have a very quick check. Yeah, you can see there's this board check. So what it is trying to do is we are not going to run any simulations over here. Yeah, what we are going to do is, you have these transmission lines, and then, you try to route it, yeah, until you see an edge over here. And then if let's say we are trying to use a board check, then it's going to give us a violations or warning. It says that, okay, this is not, this doesn't look good. Yeah, you have to probably change it. Why is it like this? If let's say we try to analyze it from electromagnetic point of view, you can see that, here you are seeing a perfect microstrip lines. But then if you come to here, somehow the ground is not complete enough. So it means that when you're coming to here, the impedance at these locations is somehow different from what you are seeing here. And of course, when you are seeing different impedance, means that you are going to see discontinuity. Then you are going to face some problems in your SI. You are going to see problems in your EMC, like, conducted emissions or even the radiated emissions. Okay, so what we are going to do in this CST board check is, of course, we have to know which net you want to check, right? So this is what we are showing here. We have to tag the nets, and then we have to tag the components. Why we have to tag the components? Simply because, for instance, in EMC, people used to have these decoupling capacitors. Yeah, they have to put it somewhere so that they are able to solve these EMC issues. So capacitors itself, it actually has a lot of values. Yeah, so some capacitors, yeah, you use it for the charging, discharging. Some you use it for decoupling purposes. So we have to tag it properly as well, so that we are going to use this rule checking in a very proper way. Okay, and of course we have to check the rule sets as well. For instance, I have this transmission line. I can send it. I can transmit a very slow signal, or I can send a very quick signal. Yeah, it depends. It depends on your application. But if let's say you are transmitting a very slow signal, somehow the requirements on this particular net is not that not that tough, not that stringent. But then if let's say you are going to a signal net that is transmitting a data that is very fast, then we have to be very careful with all this. For instance, they are very particular about the spacing. They are very particular about, the distance between here with the edges or things like that. So these are all the rules. Actually, we can find it inside this board check. Okay. So as soon as we are done, yeah, we can actually, export this 2D model in a 3D, yeah, like what you're seeing over here. And then we are trying to simulate with the transient solver, frequency solver. So this is actually the same like what we are doing in the antenna. presentations a while ago. Yeah, you can see you try to use the transient solver, you try to solve them, and then in the end you are seeing the few results, S parameters, etc., and etc. Okay, and of course for PCB, yeah, we also try to analyze with a few very specialized solver. Yeah, so whenever you are dealing with PCB, yeah, it is not exactly the same idea like what you are seeing in this full 3D full wave solver. So what they are doing is, you know, you have so many nets inside these PCB boards, right? So we do not want to set up one by one. Yeah, this is going to be troublesome. So what we do is, you know, we have this SI analysis, PI analysis. It actually simplifies the entire setup time. Yeah, this is the reason or the main reasons why people would like to use PCB Studio for most of the analysis for the PCB. But it doesn't mean that we are not going to use 3D. We are still going to use it, but it's under circumstances where, let's say, yeah, where you have these signal nets, yeah, they are transmitting data that is very, very fast. Yeah, probably up to, you know, few gigahertz, or probably, you know, they are transmitting like a 5 gigabit per second, things like that. So in that case, yeah, we have to use a full 3D solver. Okay, so first thing is let's try to look at this power integrity. Yeah, power integrity, like what I mentioned just now, is just to look at the quality of these power planes. For instance, I have these power planes. I have this board, for instance, and then you know, inside here you probably have a few power planes. Yeah, you may have the power planes islands of 1.8 volts. You may have a 1.5 volts. Yeah, you may have 3.3 volts, etc. and etc. Yeah, so this is what you mentioned by power planes. And of course, you know, there are many ICs located onto these particular designs. Okay, some of them, they have to share the same power planes so that they are able to power up their IC, right? Okay, so we have to look at the quality of this. Yeah, why is it like this? I'm going to explain later. Okay, so look at here. Yeah, for the PI analysis, there are two things you can do. The first thing is the IR drop. The second thing is the PI solver. Okay, so IR drop is nothing but just a simple, you know, V equal to IR. Okay, so you have, let's say you have this source, 1.8 volt. Yeah, and then after that, you need to supply this current to an IC, let's say operating at 1 volt. Okay, so you need to go through, let's say, a VRM, voltage regulator module. Yeah, and then you probably have some decaps along the way, and ultimately you need to supply this voltage source to this IC, right? So if, let's say, along the way, yeah, let's say along the power plane lines, the impedance is very high. If, let's say, the impedance is very high, so it means that you are going to have a voltage drop along these particular planes, which is our power planes. Then in the end, you know, the voltage drop that reach the IC, it will suffer a little bit. So it means that you are going to see something like this. Initially, when I supply is this voltage, but then when it reach the IC, I'm reaching this voltage. So in the end, the output coming up from IC, you'll be at this level as well. It's not going to be at this level. So it will actually deteriorate the performance of our received signal in the end. Okay. And then when we talk about this PI is something like, you know, high frequency. Okay. So remember, we have this voltage source, they are supplying DC voltage. But then we have to look at something called AC or high frequency. Why? It's because I have this IC. When I power up this IC, yeah, it actually needs to work. Yeah, it needs to generate output, which is 1010 signal. Okay, so when you have outputs of 1010 signal, somehow if you try to look at the currents, yeah, it actually, you know, there's a sudden change. Yeah, because if, let's say, you have a voltage that changed from 0 to 1 or 1 to 0, yeah, somehow there's a sudden change of your current. And then if, let's say, you try to multiply with the inductance that is caused by your power planes, so in the end you are going to see this noise. Okay, so this noise is very, very hazardous. Yeah, is impacting a lot because on the same power planes, they are all sharing the same voltage source, right? They are sharing the same source for the voltage. Okay, so in the end, if you try to look at the other IC, when you power it up, you are going to see a lot of noise because this guy somehow transfer the noise to the other IC in the same particular board. Okay, so these are some results on the power integrity, yeah, where we are trying to look at the impedance across some frequency range. For instance, you know, from kilohertz up to 2 gigahertz, something like that. Okay, So let's talk a little bit about this IR drop. Yeah, like what I mentioned just now, it is just a very simple V equal to IR. Okay, and then for a typical system, yeah, we have this connector is probably connected to your, power cable, and then we have this power battery management system, yeah, and then they are connected to this VCS net, and then we have a voltage regulator, like what I mentioned just now. We have to split the voltages because some ICs they are operating at 1.8, some ICs they are operating at 1.5. Some ICs they are operating at 3.3. So we have to split the voltage drop. Yeah, we have to split the voltage to different power planes. And then in the end, yeah, this supply will be connected to the IC, and then we are able to power it up. Okay. So as you can see over here, if we try to simulate this in our PCB studio, yeah, they are going to tell you, yeah, how much voltage drop that you are monitoring at this pin, for instance. U1 pins at pin number 1, for instance. Yeah, this is the voltage drop you are getting. Yeah, and then this is IC U5. You are going to see this voltage drop as well. Okay, and of course there are some requirements. Sometimes you try to set the tolerance. Let's say this is 3%. Yeah, we are able to pass. But if let's say you try to make it very strict in terms of the tolerance, then we fail it. Okay, so this is going to give us problems. So the goal in this case is, we want to reduce the impedance on these particular power planes. Okay, and of course, besides that, they are also calculating this power loss on the components for you. For instance, in these power planes, you do have resistors, you do have capacitors. So they are going to calculate for you the power loss on that particular components. So it means that later on, you can actually proceed with the thermal simulations. Okay, so these are some color plots, yeah, on this IR drop. You can see that these are the locations where you are having a very high voltage or high power loss, something like that. So it means that if let's say you want to improve the designs, so this is somehow the locations where you should consider to optimize it a little bit. Okay, so the next thing is we like to go with this PI analysis. So PI analysis is exactly the same thing because we are talking about the same power planes. So the only difference is we are talking about non-DC, yeah, is AC. Okay, so what you can see over here is, ultimately we have this IC. Yeah, this IC is going to be power up, and then in the end, I have to generate 1010 signal. Yeah, I have to generate outputs. I have to generate outputs. I have to generate data so that I am able to communicate with other people, other ICs, for instance. Okay, so as usual, as you can see over here, yeah, they are trying to use Decap so that they are able to solve these noise issues. Okay, so the noise issue I mentioned just now is, when you try to generate 1010 outputs, there's this DIDT. There's a change rates of your currents. Okay, and then if you take this, you multiply with the inductance on this particular area, then we are going to get noise. Yeah, so this is a noise where we have to try to minimize. Okay, so these are some settings. Yeah, I'm going to skip this. Yeah, because ultimately what we need to do is, we just need to select some pins, and then you have to tell them whether you have already included some decap inside there, and ultimately we are able to get a result like this. So this is a typical results from the power integrity. You can see that at this frequency my impedance is pretty low, but if you try to go up a little bit, you can see that the impedance is getting higher and higher. Okay, why is it like this? Yeah, because that is the nature of the inductance. Yeah, inductor, it originally looked like this as well. But then you see, we know the inductance looks like this. But then if you want to bring this down, yeah, we need decoupling capacitors. Yeah, if you have decoupling capacitors, what you do is, they'll just bring this value down. So it means that we are able to shift down the impedance at high frequency. Okay, and when we are using these decoupling capacitors, so in actual case, yeah, we do have this ESL, parasitics elements. But then in simulations, we actually have the options whether you want to include these parasitics or not, right? So yeah, just be careful with this, okay? And then these are some results. Yeah, you can see that, okay, let's say you see some, let's say here we are seeing some peaks. So this is a peak, we have to bring it down, right? So what we can do is, you go to this color plot, then you see, yeah, this is a place where we actually have, wrong, very high resonance or strong resonance. So what we can do is, we can actually put decoupling capacitors at these locations, and then we should be able to bring down the impedance at this particular frequency. So same to this as well. Okay. So the next thing is, we have this very interesting tool. Yeah, we have this Decap tool. So what Decap tool is trying to do is, for instance, in your original board designs, for instance, this is your original board designs. So you try to put a lot of decoupling capacitors, because we know that as a rule of thumb, if you try to put a lot of decoupling capacitors, definitely this is going to come down. Means you are going to get a very low impedance. But the problem is, some people, they actually do not do that much of analysis. They simply put everything in. So in the end, yeah, you may end up having, 40 decoupling capacitors or even 100 decoupling capacitors. So if, let's say, from OEM point of view, yeah, this is not going to work. It's because we have to spend a lot of money on these capacitors as well. So what we do is, we have to optimize. So we have to optimize, yeah, at that locations, yeah, you need these decoupling capacitors or not. Okay, if you don't need, we are going to take it out. If you need decoupling capacitors, the next thing is we are going to choose for you, yeah, which value you can use at that locations. So this is what exactly Decap tools is trying to do. Yeah, you can see that, I actually chose what are the capacitors I have, yeah, and then I just tell them, yeah, with these original designs. So get me a impedance that I want, and then tell me how many capacitors do I need to use in this case. Yeah, so is something I would say very convenient. Yeah, is very efficient in terms of optimizing the power planes. Okay, so next we shift a little bit to the conducted emissions. Yeah, I think I will shoot quite a lot. Okay, so let me try to go a little bit quicker. So conducted emissions, yeah, is more about the measuring the noise from this device back to my listens. So listen is just a device that is able to detect the reflections or the noise coming back to the DC source. Okay, so what happens is you have this DC source, you connect to listens, and then this listens output, yeah, they will be connected to DUT over here. So this is actually connecting your power. You want to power it up, but then most of the time when you have this conducted emissions issue is actually due to this switching modes power supply inside your device or inside your products. Okay, so you need to generate a very stable DC output so that you are able to power up all the ICs over here. But the problem is in the generations over here, you actually have the switch. Yeah, you switch it. So in the end, this noise, you will actually couple back to these listens. Okay, and then we have this EMI receiver, yeah, connected to listens. Yeah, we want to measure how much noise that is coming back to this DC source. Okay, why do we need this? It's because let's say you have a power plug at home. Okay, and then you actually need to connect to many devices. Okay, if let's say this guy is generating a lot of noise coming back to my DC source or power source, then it will actually propagate this noise to other devices in the system as well. So it means that you are actually transmitting back your noise through the power cable. You are influencing other people. So that's why this is actually one of the important aspects in terms of conducted emission as well. Okay, so look at some results. Yeah, so in EMC, people always talk about this kind of spectrum. Yeah, and then you can see, this is probably the switching frequency of your switch. Yeah, and then coupled with these problematic power planes, then we are seeing something like this. Okay, so what we can do is, as usual, yeah, if you are familiar with the 3D EM simulations, what we can do is, we go to the problematic areas. Yeah, we try to observe what is the frequency points. Yeah, and then in the end, we try to look at the field plots. Okay, from here we can know that, yeah, this place, yeah, probably, yeah, it has a very high impedance. So what we need to do is we can probably put some decoupling capacitors at these locations, and in the end, yeah, we can actually get a very good results over here. Okay, and of course, if you are dealing with the if you are dealing with the EMC simulations, we have to always deal with circuit simulations. Yeah, because in order for your PCB board to work, yeah, you need to have circuitry, you need to have ICs so that they are able to transmit some signals. Yeah, and then you have to integrate that with the performance or parasitics of your PCB boards. Okay, so that's why you can see that for this particular model, yeah, we can have these PCB boards layout, and then we have to connect with all these red cones. These are all our discrete ports. Okay, so these discrete ports are eventually connected back to our components over here. Okay, so in the end, we simulate everything, and we should be able to get the results or the noise that is coming back to the listens. Okay, so this is actually some results that we observe at the inputs over here. Yeah, so this is what we are measuring at the listens. Okay, and then we are also measuring some voltage signal at the CPU one, as you can see over here. Okay, and then we try to optimize over here. Yeah, initially we get a very bad results, but after that we look at this frequency, we look at the field plots, and then in the end we know where should we put these decoupling capacitors. And then in the end, after we put these decoupling capacitors, we are able to bring down the radiations at this particular level. Okay, so next is a radiated emission analysis. Yeah, is something quite similar. It's just that we are looking at different frequency range. For instance, in these radiated emissions, we are talking about gigahertz. But then for these conductor emissions, we normally talk about up to 30 megahertz. Okay, so you can see that when we are going to radiated emissions is 30 megahertz onwards. Yeah, some people they try to look at 1 gigahertz. Some people they will try to look at even higher frequency. Okay, so basically it's the same thing. Yeah, we want to inject this voltage source onto this particular system, and in the end, when this guy is operating, we want to look at what is the radiations into space over here. So that's why we have antenna over here that is placed normally 3-meter distance from this device. Yeah, and then we are able to get the result like this. Okay, so what we are doing here is we are not going to do like what measurement is doing. So what we are doing is we are going to put some probes over here. Yeah, and then we are going to capture the radiations onto all these probes, and in the end we are going to capture the maximum value. So that is what we are doing in the measurements. Yeah, so there are a few methods for us to perform this radiated emission analysis. Yeah, of course, we are trying to simplify the simulations. So what we are doing is, we just go back to the conducted emissions simulation results. Yeah, we know that what are the noise that is coming back to listen, right? So what we need to do, just take the signal, and then we just inject over here. Yeah, because we know normally the radiated emissions problem is coming from the wire. Okay, if you need something to radiate, you need antenna, but somehow you do not see any antenna inside your device. So as soon as you connect this cable onto my device, so we are seeing a very long cable. So long cable is somehow acting as antenna. Yeah, so that's why we are able to radiate something out. So in short, yeah, when we are doing radiated emission analysis, we need to connect cable, because first thing is in measurement itself, yeah, they are trying to connect cables, so we have to make it equivalent. And second thing is, when you connect cable with different length, yeah, they are going to give you different result as well. So this is something we have to be very, very careful about. Okay, so the next thing is we talk about this RF interference. Yeah, you can see, this is a normal PCB boards we have, and then we have antenna, we have these transmission lines. Yeah, for instance, now I would like to transmit signal on these transmission lines. So is this going to disturb my antenna or not? So this is something we call as a RF interference. Okay, so somehow, yeah, we can even try to put in the actual signal of this particular signal nets. For instance, I'm transmitting USB signal with certain data rates or things like that. Yeah, so this is something we can do, and so we can try to analyze in the RF interference task as well. Okay, so these are some simple results with the our T solvers. Yeah, you can see we are getting the S parameters for this antenna, and of course for antenna, most of the time, yeah, people will try to use impedance matching, yeah, so that we are able to get very good performance. It depends on the designer anyway. Yeah, and then what we would like to analyze is, for instance, yeah, you have these transmission lines. I would like to move this antenna from here to here. We like to look at how much is the interference. Okay, so you try to look at here. Yeah, this is somehow the coupling. Yeah, at different assemblies. Yeah, and at different location as well. Okay, so this is some few monitors. Yeah, I'll try to make it a little bit quicker. Yeah, so this is what I mentioned just now. Yeah, where we are going to excite with the random signal. Yeah, this is PRPS. So this is the results we are getting. So if let's say I would like to transmit with the data that is very slow, fast, very fast, then somehow the interference, yeah, the coupling into the antenna will look different as well. Okay. Okay, and of course, we can, yeah, we can look at this directly. Yeah, for instance, if let's say you talk about these radio definitions, let's say you have this antenna over here, you have this antenna over here. Yeah, there's a sensitivity for all these components over here. So we have to make sure we are able to fulfill them. So if let's say, if this guy is not sensitive enough, yeah, I am transmitting a lot of signal that's coupled to here, but somehow this is not very sensitive, then eventually I'm not picking up the signal. But if let's say this guy is very sensitive, yeah, a little bit of very weak signal that's come to here, then I am already able to pick up at this particular antenna. Then this is going to give me a problem. So that's why in order for us to analyze RF interference task, we have to understand the sensitivity for every single systems over here. And then in the end, we are going to get this violation matrix. So for instance, yeah, I have this Wi-Fi 2.4 transmit. So am I going to interfere with this technology? Am I going to interfere with this technology or not? So after you run this RF interfering task, we are able to get this violation matrix over here. Okay. Okay, so let's go to the last one. It's about the thermal analysis. Okay, so thermal analysis, as usual, yeah, we would like to focus a little bit more on these EDA boards, yeah, or these are layouts. So this is actually the sample we made ourselves, yeah, because we want to verify the simulations and measurement results. So look at here. Yeah, this is the thermal analysis we are proposing. Yeah, first one is we can try to analyze with the DC, and the other one is we can try to analyze with DC plus AC. How do we do that? Okay, so let's say now we have this particular board, yeah, and then I would like to start with our IR drop. So what we do is, we have to, of course, run the IR drop analysis, yeah, and then all these components over here, we are going to represent with some shapes over here, okay? And of course, if you want to deal with this thermal analysis, we have to look at how much current that is supplied to our load, right? If let's say the load conditions is 1.5, yeah, I would say the currents that exist inside these power planes is going to be not so much. But if let's say we try to increase the load conditions to 5 watts, yeah, probably the current that's flowing onto this board is going to be a lot. And then when it multiplies with our, the copper on these power planes, then they are going to have voltage drop. Yeah, it's going to be hot as well. Okay, so let's try to look at the results from our IR drop solver. Yeah, you can see we can already calculate how much power loss on all these components over here, how much they are. Okay, and then we perform measurements over here. Yeah, we try to connect a load over here. So this is a USB connector. So what we do is, we just connect, let's say, hard disk, external hard disk, and then we just try to measure the temperature at every location over here. Okay, and so you can see when we try to set the load conditions to 1.5 watts, for both models, yeah, we are able to get this kind of results. They are actually quite close to our measurement results, yeah, except for this one, okay? But if let's say when we try to increase the load to 5 watts, you can see that the discrepancy has already gone up by a lot, okay? So I would say that is still not too bad, yeah, it's more than 10 to, in the range of 10 to 20%, yeah? So it means that if even with the IR drop solver, we can already get a pretty decent thermal results, okay? But I think this is not sufficient. So what we have to do is, we know this is actually a DC-DC converter, right? This is the DC source. And then we know that this guy, yeah, the switching over here is actually consuming a lot of power, okay? So what we try to do is we run this conducted emission analysis, and in the end, you like to observe the voltage and also the currents at these particular components. So what we are seeing here is, we have the voltage informations, we have these current informations, and in the end, we just multiply V and I. If we multiply V and I, so in the end, we are able to get all this. So these are actually the power loss at different harmonics. So what we have to do is, we just add up all these power loss, we add up everything together, and then of course we have to add these power loss at the components that we mentioned just now. So in the end, you can see that after we do this, yeah, we are able to get a very good correlations with our measurement results. Okay, so that's what I want to share for today. Yeah, it's a bit compact, but I think it is meant to provide you a general overview on the EDA analysis with the CST. So in case if you need to have further discussions, if you want to understand a little bit more, yeah, you can always contact Kat. Okay, so she will collect all the questions and then she will come back to us. And we will try our best to answer your questions.